afternoon, everyone. I'm Chun-Yu Lin from National Center for HPC in Taiwan. And today I'm very glad to share my report about the simulation of collective neutrino oscillation. This is a really kind of new project that I collaborated with Institution of Physics, Academia Sinica, and the GSI. They are the main domain knowledge driver for this project. And since last 2 years, we intend to push such kind of calculation to a more realistic time-dependent cases that allow us to discuss more interesting physical problems. So today, basically, we develop code from scratch. And today I will focus on the single node optimization via the compiler directives like OpenACC and OpenMP. So the neutrino is the fundamental particle. It can oscillate even in vacuum. It can change from one type of neutrino to another type of neutrino. This is a very, very strange property that no other fundamental particle can have, like electron or proton. Today's topic, the collective neutrino oscillation, is another kind of microphysics that can cause such kind of oscillation that can trigger the flavor instability and the Buck flavor conversions. Basically, it is due to the self-interaction in the neutrino-dense systems. So people expect that it's important for extreme astrophysical scenario like supernova explosion, neutron star merger, or nuclear synthesis in the early universe, the Big Bang. So if you look at the current full-scale supernovae simulation like this plot, basically what we are studying may be important just outside the central red core of the explosion, where the density is high enough, but not too high to allow such kind of microphysics dominate. So basically, this is where we are most interested in that kind of research. So this is a really active research field recently that people are just starting trying to figure out what kind of problem we can solve and what kind of scenario we can solve with current numerical code. There are many things unclear. And this property basically is originally from the full quantum physics. So the full equation is kind of complicated. It involves many body physics. So what we are actually solving is a mean field quantum kinetics equation that is basically the Boltzmann equation for the phase space density matrix. So the full equation is just look like this. It is mean field quantum kinetics description, ignoring the high order terms. So it involves the x derivatives and the p momentum derivative and involving some source term and collision terms. Now, we usually assume that, well, this equation can first simplify. We usually assume that neutrino doesn't suffer from, say, the gravity or electromagnetic force. So we assume that it is faultless, so we can ignore the momentum derivative terms. And then we also interested in so-called free streaming limit, such that we don't consider the absorption or emission of neutrino. So we are just consider the natural quantum evolution of neutrino. So we can also ignore the collision term on the right-hand side. So basically, the equation is pretty much look like a very simple, well-posed hyperbolic system, because if you look at the principal part, it is just the advection equation, where the v is just a constant. So there are many numerical tools actually can help on this. And if you look at the right-hand side, this bracket is actually the commutator. AB bracket is equal to AB minus BA. So basically, that means that the right-hand side is actually traceless if we ignore the collision terms. But in practice, we are still consider trace part just for checking of numerically. So I think one of the challenges is that the component has many. If you look at this matrix value density matrix, it involves 9 real components for the neutrino and another 9 for the anti-neutrino. So totally, for the full 3-flavor system, there are 18 partial differential equations. Even if we restrict to 2-flavor system, that where we only consider 2x2 matrix, there are still 8 coupled PDEs. So I think that's caused a lot of memory challenging to the simulation. And for the right-hand side, each term basically represent the different physical mechanisms that cause such kind of oscillation. For example, the banking oscillation, the oscillation due to the matter turn, where the neutrino interact with matter like the electron. And the most important turn is due to the neutrino self-interaction, which is main target today. If you look at this is the most challenging part because it involves the momentum integral. Naively thinking, it may make your simulation loop even deeper. But in fact, this factor is just a common integral factor independent of momentum, but depend on each space-time point. So we can just pre-compute this common integral factor for each space-time. So the downside is that the main nesting loop over x and momentum is not tightly nested. So that's caused some challenge into the OpenMP parallelization or OpenACC parallelization. So in this case, a simple 1D evolution involved a loop over x and p. So basically, it is a loop with level 2 at each time step. And if you look at the right-hand side, it seems the arithmetic intensity is not really high. So that may also cause some challenge to the performance of this code. So we are really interested in the long-term evolution of the flavor conversion. So if you look at this picture, basically it involved some different initial condition and the different neutrino contents. And we can look at how the flavor wave convert or how they depolarized in different cases. For example, initially, if we just put some central perturbations in a point, then as a simulation style, you can see that for different kind of neutrino content, where the alpha equal to 0.9 means basically the neutrino is much more abundant than anti-neutrino. And alpha 1.1 is the case vice versa. So you can see that for this case, initially the perturbation can cause some flavor wave pattern and some buck flavor conversion from the electron neutrino to another type of neutrino. So you can see some buck conversion region in different momentum range. And for some region, there are also the situation that you can see that they can just look like random because in that case, the different type of neutrino are just randomly distributed. So we call it depolarized. At the right-hand side is another case where we initially put random perturbation for the electron neutrino. And as the time goes by, you can see some pattern just grows up. And we see some build-up of flavor conversion in this kind of system. So that kind of research may be important inside the supernovae explosion simulations. Even currently, there are some detail that people doesn't really very clear about what caused the supernovae explode. So we hope this kind of research can provide some insight to that. Okay, so the numerical method we use is quite standard. We developed a package, the collapse oscillation simulation engine for neutrino to solve this kind of problem. Basically, that is based on the method line approach and arcade for time stepping. And we adopt two different approach to treat the right-hand side. One is a very simple central finite differencing plus some artificial numerical dissipation to handle the instability. And we also implement a finite volume version with the Wayne reconstruction, which is a kind of popular method used in this field. And currently we use unified mesh with periodic boundary condition. For the data layout, we use a standard structure of array data layout. And totally, there are roughly 15 components of field, which involve 8 fields. And because we need to do the arcade for time stepping, so there are 4 times amount of this field. And for the Wayne reconstruction, for each field, we need the left and right flux for the calculation so that add another 16 components. So it causes kind of severe memory imprint for this kind of calculation. And it's also important to choose the correct data layout for better memory infinity. So we put the momentum dimension to the last index of the 2-dimensional array because that will have a better memory affinity basically for the interaction, we took a very conservative OpenACC and OpenMP internal parallelization without using any advanced things like SIMD function or CUDA PDEs. And recently, we also joined a co-comparison project to other groups where they use different kind of numerical method, and we basically get the very consistent result. Because what we are simulate is really, sometimes it's not really intuitive to understand. So we really relied on some code validation scheme to check the validity of our code. So we rely on the domain experts to tell us that which quantity is conserved. For example, in this kind of systems, we require some conservation among this variable, for example, the polarization vector of the neutrino contents. We also enforce that the lepton number conservation, which is a property in the weak force system. And we also need to find some exact solution like the vacuum oscillation to check if the simulation can reproduce the exact solution. And finally, of course, the conversion test is very important to check the correctness of numerical scheme. So basically, for both of our finite difference implementation and the finite volume implementation, we can really get the expected convergence for both schemes. So basically, those give us a confidence that these codes are really correct, and we can base on that to discuss more interesting problems. And this slide is just the on-site visualization for the finite difference scheme and the finite volume scheme in our case. As expected, we expected the most of the time are spent on calculating the right-hand side for finite differencing. And for finite volume, it even spent a lot of time in the Weno reconstruction. So these two functions basically took the most fraction of our simulation if we didn't consider the output and the analysis. So for the finite differencing, you can very see clearly that within the RK4 step, there are 4 sub-steps to calculate the right-hand side. And for finite volume version, before the main function to calculate right-hand side, we also need 8 Weno reconstruction subroutines for each neutrino field. So basically, this gives us a glance how the routine organized in the code. And we use the very conservative standard OpenACC, OpenMP directives for the parallelization. So basically, we utilize the unified memory in OpenACC. And for data movement, we really relied on the OpenACC's enter and exit data class to handle the initialization and the movement of the data automatically. So it's almost give us a free lunch to parallelize our code because by only adding those tags, we can really get a acceptable parallelization. And I would like to mention that I really thanks to the Matt and Manson for their help in the OpenACC hackathon last years. And for our main loop, we really get a good time to solution. This is a scaling test for the CPU run on different core. And basically, they are mostly depend on the dimension of momentums. And as I mentioned, because in each main loop, we need to calculate the common integral factor from the momentum. So this actually destroy the tightly nested property of this loop. But even that, it seems that we still get a pretty good parallelism. So this is our basic testing benchmarking for the single node performance. So we use the time per step per grid as a performance matrix because this matrix is really stable for large enough a problem. And this number is only slightly dependent on the size of momentum. So we use this number to characterize how good the code is. And this is a scaling test for different problem size. On the A100 GPU, as you can see, the performance is quite stable. And the right-hand side is the scaling test for the multi-core case. So for different methods, we can get from 2 times or 5 times speed up compared to one CPU node to one GPU. It is a great boost for our research. And finally, in order to probe to see if our code can really utilize the hardware capability, we did a really simple hierarchical roofline analysis on GPU. I used the empirical roofline tool developed by Berkeley National Lab, and we used the NCHC compute to collect the performance counter to calculate the number of flops and size of data movement for each kernel. And we can calculate the arithmetic intensity for different kernels. As you can see from this dot, most of kernel are memory-bound kernel, except for the Wiener reconstruction. It almost reached the empirical top roofline. And it seems that the L2 cache utilization for major kernel like the calculate right-hand side and the Wiener reconstruction are quite good. But it's still far from good because it seems we still have a lot of room to improve that. So, but this really gives us a really good guide to which direction we might be improve our code. And there's a note that high flops may not imply good implementation because it happened that in our earlier versions of the code, we used some bad implementation by calculating the interaction turns with another level of loop. And it gives us a lot of redundant calculation, and it gives us a higher flops and better performance, better parallel efficiency. But it turned out that most of our calculation are the redundant calculation. So it's really important that we need a good implementation before we really optimize those things. So to conclude, with this code, we can really begin to explore some interesting neutrino microphysics dynamics in dense neutrino system. And we use method-blunt method, archival, and we implement finite difference and finite volume in this version. And OpenACC, OpenMP really provide flexible baseline for single node optimization. It is appealing for projects like us that is in the development stage, and we are basically kind of fundamental research. So many things are subject to change. So this really gives us the opportunity for the rapid numerical experiment for different methods and the diverse parameter space. And the roofline analysis indicate the memory-bound nature of our problem, suggesting runs for improvement toward the extension, the future work to multi-GPU and multi-node code. So thank you.